Okay, so you guys remind me, what is an intermolecular force? Things holding solids and liquids together. Yes. Do they exist in gases? In the ideal gas model, they don't exist. In real gases, they do actually exist, okay? That's how we're able to take and compress a gas into a liquid, right? They have to exist there. So yes, they exist. Stronger or weaker than chemical bonds? Weaker by about a factor of 10 usually, okay? They're on the 10s and 20s of kilojoules per mole, and usually bonds are on the order of hundreds of kilojoules per mole, okay? We talked about ion dipole, so salt water is your go-to there for the model you want to think about. We talked about dipole, which is when we have polar things that have that asymmetric symmetry, and we talked all about that last time too. We talked about hydrogen bonding, which is a special kind of dipole. You got to have hydrogen, and that hydrogen has to be bonded to nitrogen. What's the other stuff? Oxygen. Fluorine. And fluorine. Yeah, NO and F. Because of the electronegativity of those things, right? So nitrogen, oxygen, fluorine, really, really electronegative, pulls the electrons in that bond toward itself. If you've got a hydrogen, it's just a proton and an electron. And so you've got a almost whole proton sticking out in space, so you see almost a whole charge. And that's why we see such a strong attraction in hydrogen bond. Now we want to look at dipole induced dipole. This is where you're going to see polar things interacting with non-polar things. So we can ask the question, why would something like iodine or oxygen dissolve in water? Right? We told you last time when we talked about dipole stuff that polar things dissolve in polar solvents, non-polar things dissolve in non-polar solvents. So now I'm lying to you at some point in time, right? Either I told you a lie that polar things and polar things, or this is a lie. Turns out we can make non-polar things dissolve in polar solvents. They don't do a very good job of it, but we can make it happen. And it happens by inducing a dipole. So if we have water, for example, and we're dissolving oxygen in water, where does that happen? Where would that be important? So you say, anybody got a fish? Yeah. Right? If we didn't have dissolved oxygen, we wouldn't have fish, right? So the way it works, you've got this polar thing, you've got the oxygen that's nonpolar, but the water is going to induce a dipole in the electron cloud of the oxygen. So think about what the oxygen molecule is, right? So there's an O, and there's double bonded to another O, and then we got all these electrons around it like this. And so if we look at it, it's a cloud like this, right? The electron cloud, roughly spherical thing. Well, that ain't spherical at all. Pretend it's spherical. So now we're going to bring in a water molecule, and the water molecule has either positive side where the hydrogens are at, or negative side where the oxygen's at. And those are going to interfere with the electron cloud of the oxygen. It's going to kind of distort that cloud. Okay, it's kind of like that cloud gets blown around in the breeze, if you want to think about it that way. And once that gets distorted, now there's an asymmetric thing there, and that asymmetric thing is then polar for the moment. So something like this, right? We bring in our water, we let it interact with that electron cloud around the oxygen, we shift that electron cloud. That shift is called polarization. And now we've got an unequal sharing of electrons between these two oxygens, even though they should be equal, right? But now we got a slightly positive place and a slightly negative. The bigger the thing is that we're putting in the water, the bigger its electron cloud it is, the easier it is to wiggle that electron cloud around, right? So something is like iodine versus chlorine. I2 is a lot bigger, right? Because the radii of iodine is bigger. Their electrons are further away from the nucleus. What do we know about electrons that are further away from the nucleus?
They have shielding.
They do have shielding, which makes them easier to take off, right? So they're not held as tightly to the nucleus because they're further away. So they're also easier to wiggle around. So how much you can do that, how much you can distort that cloud, is called polarizability. And again, the bigger the thing is, the more easily it is to be polarized. And again, it's just because the electrons are further away from the nucleus, they're not as tightly held, and so they can wiggle around. Kind of give you an idea of that, we've got three nonpolar things here, hydrogen, nitrogen, oxygen. As we increase their molar mass, they're getting bigger. And as we increase their molar mass, where solubility is going up. Oh, so yes, these are diatomic molecules, but absolutely, you can have this with what? Like any type of small chain organic molecule, you can see the same thing going on. Yeah, any nonpolar thing, like carbon dioxide, for example, right? Carbon dioxide is dissolved in water as well. It doesn't have to be a diatomic thing. All our examples so far have been diatomic. All right, here's a question for you. All right, which of the following is more polarizable, or is the most polarizable?